if you had quantum encryption, you could know if someone snooped on your communication.
Oh, because it would affect the electron or whatever.
Because it would alter it, and then you would know, oh, hey, someone's snooping. Well, it turns out you actually can trick quantum encryption. So, for example, the Fermi labs in California have done over-the-air quantum encryption using two photons or two electrons.
Yeah.
They'll entangle it, they'll send one off to like 100 miles away, and they can like modify one on one end, and the other end does something. And so quantum encryption is something that's real. It's not practical today, but it's real. People have tested it, and it works.
Welcome to Practical AI, everybody. My name is Jeff. I'm here with Peter Lynn. We are sponsored by Pocket AI. Pocket AI is a tool that you can use to edit the weights of your model. With Pocket AI, if you prune your models, you can get 60% of the weights eliminated, which should improve accuracy and definitely will not decrease it. Peter, today we are going to talk about quantum computing. Looks like Google has been in the news a little bit lately, and they came out with something called Willow. So tell us
Yeah.
what hit the wire here recently.
Yeah, so Google's been working on quantum for over a decade now, along with IBM and several other research universities. And so basically, they've come up with a new chip that does quantum processing using qubits. Um, it's actually kind of light on details, so they're just saying, hey, we've managed to scale this up to 101, it's 101 or 100 qubits. And so it's a significant breakthrough because historically, and this goes back to kind of classic computing versus quantum computing. So in classic computing, things are either on or off. It's either 0 or 1. Whereas a qubit, which is basically a photon or electron, it's spinning, and it's not a 0 or 1. It depends on how you read it. It could be spinning right, left, up, or down. And if you count diagonals, then there's even more. And the problem with quantum is you can write data to a qubit, but it only lasts for like like microseconds. Like I think they said they got up to 100 microseconds. It used to be less than a microsecond. So microsecond is a thousandth of a millisecond, right? So these are like super short time periods. And that meant that if you wanted to do some processing, you would write the data to the qubits, do some processing, and then read the result. Well, if your window was in the microseconds, like if you read at the wrong time, you wouldn't get that right result. And so it's just really hard.
Okay, so for the less sophisticated brain, so you've got, I think a lot of us understand that a lot of what's happening in computing is a switch being on or off. So electricity is either passing through or it's not, and then you've got these series of them, and it just creates a lot of incredible opportunities. But it's also like it's all the bits and bytes thing, zeros and ones. So we kind of at least we've grown up in that bath. Whether or not we understand it, it's at least a familiar concept.
Yep.
And what you're saying is that with this quantum computing, that's old news, right? They've figured out a way to process or to do something that it's not either on or off, and it essentially is it's electron based, but the electron can be in an infinite number of positions as it's moving around or orbiting or whatever it's doing.
Right.
It can
Yeah.
be in an infinite number of assemblies or something like that, and so that creates um, potentially a speed benefit, right? And it
Yes.
also creates an infinite number of maybe quality benefits or something like that. But what then you said is that it's one thing to have it the electron be in a position.
Yep.
It's another thing to measure it there, right?
Yeah. Yep.
So explain why it's so hard to get that to detect it to be able to use this.
So in computer science, there's a term called coherence. So it just means that if I tell you, hold this marble, and I come back to you an hour later, you'll solve the marble, right? Like I expect it to be coherent, meaning that like what was before is the same as some time later.
Okay.
With quantum computing, that's not true. Quantum computing starts with entangling two particles, two electrons or two photons, and then you can act on one of them, causes the other one to simultaneously have the same thing happen to it. And so what you can do is you can entangle these particles and use it to process, but it's processing not just one instruction at a time, it's processing multiple instructions. So
Mm.
this is what it's parallel. So that's why quantum computing has been this like holy grail of computing, because a single qubit can do multiple operations or calculations at the same time. Regular bit cannot.
Okay.
And so as
Is
you
it
multiply
actually
1 to 10 to 100, it's exponential, right?
is it actually at the same time, or is it just so quick that it's
Like at
not?
the same time, but that's also the problem, is that it's all happening at the same time, and then you got to read it at the right time. Otherwise, forget it.
Okay. Does that mean you have to read everything at the same time? Or is it actually just sort of like microseconds that you just have to get within the right microsecond,
Well,
but
so
it's not actually at the same time?
that's one of the hard parts with quantum, is that like right now it's not something you or I can use because we're dealing with actual particles. So like if you look at silicon chips, these are like 5 to 10 atoms wide. These transistors and gates and stuff that we're creating. Whereas in quantum computing, the actual processing thing is an actual atom, an actual electron or actual photon. So that's smaller than an atom, right?
Yeah.
It's like, I don't know, I forget the math of it, but it's way smaller than an atom.
Yeah.
And so, but so being small is great, but the problem is the minute you observe it, you change the state. And so all these quantum computing systems have to be super cool for it to work.
If you can observe it, you've affected it.
You've affected it, right? So this goes back to kind of that old Feynman joke about the cat. Is the cat alive or dead? It's both. Right? So this is that paradox of like the minute you observe a qubit, you modify it. And so the nice thing, when quantum first kind of became a theory, there's the idea that, oh, if you had quantum encryption, you could know if someone snooped on your communication.
Oh, because it would affect the electron or whatever.
Because it would alter it, and then you would know, oh, hey, someone's snooping. Well, it turns out you actually can trick quantum encryption. So, for example, the Fermi labs in California have done over-the-air quantum encryption using two photons or two electrons.
Yeah.
Then entangle it, they'll send one off to like 100 miles away, and they can like modify one on one end, and the other end does something. And so quantum encryption is something that's real. It's not practical today, but it's real. People have tested it, and it works.
All right, one of the things, and we won't spend too much time on this just because it gets really complicated, but yeah, you've used the word qubit a lot, and we've
Yeah.
got in here number of qubits 105.
105.
Yeah, so what is a qubit, and is 105 good, or is it, how many do we need to get to do something cool?
Well, so let's take machine learning models, for example, right? We don't know how big O1 is. Some are guessing it's 1 trillion parameters, some are guessing more. So the question is, could you take O1 and run it on this new Willow system? Well, the answer is no, because it's only 105 when there's 1 trillion parameters.
Is there a one-to-one in terms of parameters versus qubits, in like functional or?
Well, so that's an open question. No one knows.
Hmm.
How would you even load O1 onto a quantum computer? You can't today. That's not possible. So first of all, you have to solve that problem. Like, how do you actually load useful work? Because you gotta remember, like, when you and I interact with GPT, it's seconds. It's not microseconds.
Yeah.
So that means we have to write our conversation to the system, have it retain the information for minutes or hours while we communicate back and forth. Well, today that's not possible because it's only coherent for about 100 microseconds.
It's only coherent, it's only in its position and therefore readable in that fraction of a
Yeah,
second.
right. And humans live in the seconds realm. We're not in the milliseconds realm
Yeah, yeah.
or microseconds.
Okay. So it's almost too fast. What's a qubit in this context?
So qubit is just a concept, right? It can be done with photons or electrons. So it's just a bit that's an actual particle that's spinning in a certain orientation.
Got it. Okay. All right. So it sounds like 105 may be a lot, but it's probably not a lot. So I guess
It's a breakthrough.
it's a big breakthrough from
It's
one or
taken them
five.
about 15 years to go from like a handful of qubits to 105.
Yeah. So I think that's the next question. When is quantum computing going to be relevant to something? Defense, commercial, you and me. When is it going to make its
No
breakthrough?
one knows until someone figures out a way to make quantum computing that works at room temperature. It's going to be still science fiction, right? Because we all can't have a huge refrigerator with liquid helium or liquid hydrogen cooling it.
Yeah.
It's not practical. I mean, it would look cool, but like you need a constant supply of liquid hydrogen to keep the thing cool.
Yeah. All right. So it's several years away, maybe 10.
At least 10, probably anywhere from 10 to 100.
Okay. All right. Well, that answers the question. So put quantum computing on the back burner of your brain for a little bit, and just keep an eye on the research, I guess, is kind of the
Yeah.
moral. Yeah. Cool. Well, thanks, Peter. Remember, you can also listen to Practical AI on Spotify, so you can tune in on the go. Always ask questions. We will be here to respond to them, and we will catch you next time with another episode. Thank you, everybody.